It's gonna be good, right? So now we're getting to a new topic called estimation, right? So we want to talk about estimating mu when sigma is known, right? So because of time and money constraints, difficulty in finding population members, and so forth, we usually do not have access to all measurements of an entire population. Instead, we rely on information from a sample. In this section, we develop techniques for estimating the population mean mu using sample data. We assume the population standard deviation sigma is known. So let's begin by listing some basic assumptions used in the development of the formulas. Mean population mean. All right. So let's begin by listing some basic assumptions used in the development of our formulas for estimating the population mean mu when sigma, our population standard deviation, is known. All right. So here's some assumptions. Right. So first, right, we want to assume that we have a simple random sample of size n drawn from a population of x values, right? N being our sample size, right? Two, the value of sigma, our population standard deviation, right? Of x is known. So we want to assume that we know what the population standard deviation is. Three, if the x distribution is normal, then our methods work for any sample size n. Four, if x has an unknown distribution, then we require a sample size of n greater than or equal to 30, right? However, if the x distribution is distinctly skewed and not definitely and definitely not mound shaped, a sample size of 50 or even 100 or higher may be necessary. All right. So that's that. God bless you. Toot, toot, toot.
The old standard deviation is that?
The the sigma, right? That's our population standard deviation. Yeah. But it's X is just the numbers, that make up the sample size.
It's a number, it should be normal.
Mhm. The question will tell you if it's normal or not. All right. You want a second? Okay. So an estimate of a population parameter given by a single number is called a point estimate for that parameter. It will come as no great surprise that we use X bar, our sample mean, as a point estimate for mu, the population mean, right? So a point estimate of a population parameter is an estimate of the parameter using a single number, right? So X bar, our sample mean, is the point estimate for mu, our population mean, all right? Even with a large random sample, the value of X bar usually is not exactly equal to the population mean mu. The margin of error is the magnitude of the difference between the sample point estimate and the true population parameter value. All right. So when using X bar, right, our sample mean as a point estimate for mu, the margin of error is the magnitude of the sample mean X bar minus the population mean mu, or the absolute value of the sample mean minus the population mean, right? Absolute value is a function that, let's say, for lack of a better term, turns any um thing that's inside of it, right? Any input that's inside of it, positive, right? More specifically, what the absolute value is it's a measure of how far a number is from zero, right? So the absolute value of -2 is +2 because -2 is 2 units away from zero. And the absolute value of 3 is 3 because 3 is 3 units away from zero.
That's what.
So I'm just explaining that with margin of error. All right. So we cannot say exactly how close the sample mean is to the population mean when the population mean is unknown. Therefore, the exact margin of error is unknown when the population parameter is unknown. Of course, the population mean is usually not known, or there would be no need to estimate it. In this section, we will use the language of probability to give us an idea of the sample, of the size of the margin of error when we use the sample mean as a point estimate for the population mean. All right. So first, we need to learn about confidence levels. All right. So the reliability of an estimate will be measured by the confidence level. All right. So let's get into that.
You know what, let me write things in my formula sheet while you're giving us all these.
So it's already there.
I know, but I need to understand.
I got you. Hmm.
Sure. On the sheets of five.
Which is the other kind?
Wait.
Not on me, but I might. Let's make sure it's on my last one. I'll make another copy and I'll give it to you. It's also, if you look in the announcements that we have, like it's there, all the formula sheets. All right. So sample mean, which right, sample mean. Yeah.
The mean, the population.
It's in chapter 3. You can see it all right there. All right.
So margin, the difference between sample point from the last.
The sample mean and the population mean. Right. Right.
So sample point. With the X bar, right?
Mhm.
So the population mean is the use.
Right.
And true population, which is the you mean.
All right, so let's talk about this. Suppose we want a confidence level of C. Theoretically, we could choose C to be any value between 0 and 1, but usually C is equal to a number such as 0.90, 0.95, or 0.99. In each case, the value of Z critical is the number such that the area under. Let me finish this real quick. God bless you. That sounded very satisfying. Don't you feel good when you sneeze?
Population.
Right. No, U is the population mean and X bar is sample mean. Remember, Greek is population, English is sample. Yeah. Just remember Greek, right? Greek is population, English is sample. Right? Let me make that a little bit smaller, right? So in each case, the value of Z critical is a number such that the area under the standard normal curve falling between negative Z critical and Z critical is equal to C, right? So the value of Z critical is called the critical value for a confidence level of C, all right? Boom. There's some good stuff right here. One of your homework questions is to find Z criticals. You're gonna see. I'm gonna show you in a minute. All right. So for a confidence level C, the critical value Z critical is the number such that the area under the standard normal curve between negative Z critical and positive Z critical equals the critical value, right? The area under the normal curve from negative z critical to positive z critical is the probability that the standardized normal variable z lies in that interval. That means I'm finding the probability of negative z critical less than z, which is less than z critical, and that's equal to my critical value, right?
So that's
It's from the chart, exactly. Mm-hmm. Mm-hmm. So that's
what that is.
yeah.
So the area of C,
Mm.
sorry, Lana. So you're saying that for a confidence level of C, negative Z and Z has to equal C?
I can get the C value by
Negative Z.
yes, so to speak.
Negative Z times C or plus C or?
Like I'm trying to find which what happened. Yeah,
I didn't really understand that part.
I got you. We're gonna go through an example to make more sense. Good? All right. All right. Let's look at an example real quick. It'll make more sense. The probability of negative z critical less than z critical is equal to the critical value. Mm-hmm. Mm-hmm. So
No,
what?
so what you just showed me?
What this?
Yeah.
Yeah.
The whole thing is like, C?
No. C is the area that's under the curve in between the two z values.
Right, right, I just saw that he kind of like,
Yeah.
okay, negative C, zero, C, C. Okay, and now,
Drops. Nice.
now can you show me the formula to this chart?
I got you. Let's look at the example. The example will make more sense.
Is that different? Yeah, absolutely.
I guess. Yeah.
Okay, so that says P parentheses negative Z, so the C power is
Oh,
greater than
negative
C.
z critical is less than z, which is less than z critical, which is equal to the critical value. Right?
Less than
Yeah.
critical equals C.
So
So just to make sure that I got this straight, Professor, because I don't want to fail again. So what, just one more time, real quick. P equals negative Z critical, less than Z critical equals C.
yeah.
That's what you're saying.
Mhm.
You see, Professor, if I don't fucking write this down on this formula sheet.
I got you. I got you. Huh?
Yeah. In person? Yeah, I'm gonna write that.
What's in person? Sorry? Yeah, they're both in person and online, whichever one you want to do.
That's a
Yeah,
good.
yeah. I got you. So let's look at this problem, right? It says, let us use table 3 of the appendix to find a number, right, for z of 0.9 such that 99% of the area under the standard normal curve lies between negative z of 0.99 to positive z 0.99, right? So that is, we will find z critical for 0.99 such that the probability, right, of negative z for 0.99 is less than z, which is less than z for 0.99, which is equal to 0.99. Blah, blah, blah. It's similar. It is on the formula sheet. Before I show y'all where it is, I'm gonna draw this. Yeah, yeah, write it. You got time. What?
What flavor you got? Got pumpkin apple.
Nice.
They do. That's the chapter 7.
This is chapter 8.
Yeah. Okay.
All right. So So now, long story short, look, this is 99% in the middle, or 0.99, right? If that area in the middle is 99%, this area right here, right? Then let me ask you, what is this area here? What's that equal to? And what's this area over here? Exactly. 0.05, right? Not even 0.5. 0.05, like that. Yeah. It's half of 0.01.
Write this good stuff down because I'm not following you.
I got you. I got you.
Yeah. Oh,
I got you.
yeah.
So long story short, right? I want to know what is the Z of for 99, right? Z critical 0.99, right? I want to know what is that Z value. So to find that Z value, we're gonna look at the table, right? But help me out. What am I gonna look for? What's the probability I'm looking for?
Isn't it 0.99%?
You're close. Remember that the table only gives me probabilities that are less than, right? So I'm looking for all of this area right here, right?
Why it has to be from right to left?
Always it's like that. Always.
Should I write that down?
Yeah, you can. Yeah.
So I always need to find the area from right to left?
Right. Mhm. Well, that's all that the table can give you. So I'm asking you, right? What am I gonna look up in the table?
Wait, from fracture. No. Yeah, you see what I mean? Like, it's good to write it all down so you can actually study it.
So I'm looking up all of this wood. But before I can use a formula sheet, what am I looking for? That's my question. Like, what's the probability I'm looking for from this picture? 0.99 is part of it, but what am I? Yeah, I want to know what is this in the blue circle.
So you're looking from the oh,
That's what I'm looking for, right?
so
I want 0.995. That's what I'm looking for, right? I'm gonna even add a zero there just to make it a little bit easier, right? So now I'm gonna look for that in the table. All right, so let's look at the table. Mhm. Mhm. So that is the 99 plus this extra that's right here.
but what if we
Mhm.
can't figure out that little extra is 0.5? What made you realize it's 0.5?
Oh, she told me.
Yeah, but you didn't come
Yeah.
right. I'm
Okay,
trying
look.
to follow.
You
but I'm
have
not sure I follow.
you have 99% in the middle,
Yeah.
right? And you have two endpoints, right? It has to be 100%,
0.5.
but there's two ends.
Oh,
So,
I follow you, Mara.
Okay, so from the 99 split the one in half, so it's like on each side.
Professor, we're not geniuses, so you gotta break it down like that.
got you. So there's your question, right? What is the probability to the left of Z 0.99? Like this?
Professor, you have to add it, right?
Let me lower this for you.
Huh?
So you have to add whatever's in the middle to whatever's on the left, correct?
Right. Mhm.
What is the probability to the left of 0.9?
So you're adding like these two numbers here to get it.
That's a good question, Professor, shouldn't that be a negative?
I don't know. Let's see.
Should it to the left? To the left.
Right, the area is to the left, but I'm looking up 9950. Go ahead.
So for the number, everything has to add up to 100.
Mhm.
So if there's a different number in the middle, you will have to, whatever is left from 100, split it into two.
Exactly. Very good. Well done. Mhm. So let's look at the table real quick, right? Remember, I'm looking at 0.9950, the normal distribution table. Well, I don't know. I don't know. It should be positive though, if you think about it, all right? Because look at this. No, I'm gonna show you something. What happened? The normal distribution table. I don't remember which table it is, but it's called normal distribution at the top. But look, right? Let me get another color real quick.
The areas of a standard normal distribution, that's
Yeah,
that.
that one. But look, you know that right here in the middle, the mean is 0, right? So you know anything to the right of 0 is positive, and anything to the left of 0 is negative, and this is to the right of 0, right? So it must be positive, right?
We never
Right.
find these to the right. You said only.
We can't because the table only gives us values to the left, right? And when you're on your test and you forget, there's a picture right there that tells you.
Oh, it says only to the left.
Right. Mhm. So we go down to our normal distribution table, wherever that is,
A8.
right here, right?
Letter 8.
Mm-hmm. Yep. So now, what do you mean?
I thought we only supposed to have 0.1 negative.
No. This is the reverse. I'm looking for the probability in the middle. Right. And then I'm gonna find the Z value from that. Yeah. Yeah. No, reverse. You're looking in the middle, right? And you're trying to find 0.9950. Yeah. So let's look. Let's find 9950. Yeah. Find it in the table. I found it.
But don't tell us, let us find it.
Nine what?
Oh.
9950. It's okay if you can't find it. Find as close to it as possible. That's close enough. I'll take it. Right?
No, 9950. I think 9951, like Mara said.
Yeah. So this is actually it right here, right? Between these two. So both of these numbers correspond to a particular Z value. What is that Z value? 2.5 what? 2.5, 2.57 and 2.58.
Okay. So what
Right.
are we doing?
So look,
It's 2.507, 2.508.
add them together. So it becomes 2.57 and 2.58.
2.57.
Right.
Oh, yeah, right.
Yeah. Right. So right here, this is the 9949 that corresponds to the 2.5 row, right? And scrolling up, that's the 700 for the 100th place. So that's 2.57.
2.57 plus 2.58.
Right.
And then what that is, what answer?
That's what I'm looking for.
Well, what do we?
That's the Z value.
Oh, so the.
Yeah. So, right. So Z for 0.99 is the 2.57 plus the 2.58 divided by 2, which gives me 2.575, right? Something like that. Hold on, I'm just guessing. Y'all got calculators. Hold on, let me 2.57
Why did you put divided by 2? Is there a reason?
because it's in the middle. I want 9.50 and I found 49 and 500. Yeah, it is.
So because, hold on, because I want to write this down.
That's pretty good because I was guessing.
Because you want the middle, is
Right.
why you divided this by two. Am I
Right.
always gonna divide this by two?
No. Because it was in the middle, I divided by 2.
So,
Yeah.
uh,
Mm-hmm.
uh,
That's the Z for 0.99.
0.9950.
No, 0.99. Because remember, the 0.99 is what's in the middle, right? Yeah. Yes. Yeah. Mhm.
So, how would I write that down?
Yeah. Say it again.
I'm supposed to write Z equals 2.575.
Z for 0.99 equals 2.575. So when you have the area in between, right? That's what you're looking for. All right.
And Professor, now, here's the only thing I have a problem with.
Mm-hmm.
The only thing I have an issue with is that you show us a different style in class than what you test us on. Can you please try to have a similar style for the sake of us passing class, please?
But I want y'all to understand
Do
it.
this today, and then I might just open the test and it might have a problem that's nothing like this.
What do you mean? It's the homework.
Professor,
Yeah, just open the homework. It's the same thing.
professor,
Yeah, all I do is copy and paste your homework.
professor.
Mhm.
Professor.
How are you stuck on the
The
homework?
homework is not similar to what you took in class either.
OMG, how you stuck on the homework? It's the
He
same
is
thing.
He makes it
It's the same
Professor,
thing.
you don't even do the homework.
I do.
The area between 2.57 and 2.58, you divide it by 2, and it gives you the area of 0.99.
Gives me the Z value.
Gives you the Z value of
Right.
0.99. So
Right.
you add the two Z values,
Yes.
divide them by 2.
Correct.
And those-
Because the area that I was looking for was in between, right? If it sometimes you might actually find it on a particular Z value, then you just that's the answer, you know? That. Mhm.
If it felt like 3.0, we will divide it by 3.
If it was 3.00,
Just like in the Z.
Yeah.
If it, like,
all right, say
divided by 3.
say it was like say it was like 0.5 thousand.
What? You guys told me the hello. What are you
Hmm.
talking about?
So say the no say the area that you have is 0.5 thousand. I'm just making it up. That corresponds to one particular Z value,
That's 0.
a 0.00. So that's it. Right?
And it's-
So there's nothing to add and divide by 2. That's just the when it's in between, then you add and divide by 2.
0, right?
Mhm.
The goal, we take on the Z value.
Yeah.
We divide it by 3, right?
No,
You still divide it by 2?
always, because it's gonna be in between 2 numbers. Yeah. 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 Because sometimes you have the exact Z value. You don't have to divide by 2. Yeah. 0.5 thousand.
Yeah.
No, make it
Yeah.
up right now. No, he made it like.
Look up 0.5 thousand. What Z value is that? 0.5 thousand.
0.5 thousand is at a 0.0 value.
Right, 0.00. That's it.
So,
Yeah.
so you don't have to divide by 2.
Right. There's nothing to add. Is that?
5,000.
Yeah, yeah.
So
Yeah.
he's telling us what happens if there's 2.
Yeah.
Okay, so
If it's in between 2. Yeah. Mm-hmm. Awesome. All right, let's keep it moving.
The homework be diabolical in homework class.
Nah, the homework is mad easy.
No, it's not.
Yeah.
I love you, but sometimes you
Yeah.
can't even solve it for
you know
us.
you ChatGPT
Yeah.
that.
What you mean?
ChatGPT can't even fucking solve it.
Yo, wait.
GPT can't solve it.
Wait till y'all see exam 4, yo. Yo, wait till y'all see exam 4. That's about to be nice. Yeah. Mm-hmm. Yeah. Yeah.
So let me write this problem down.
I got
before
you.
go through it.
I got you.
Write it down. You gotta give me time to write it.
Got you. Well, this is just talking about what we just did, right? Mm-hmm. Mm-hmm.
Give us the practice task.
I did. You got 3 of them already.
Like, we
Ooh.
go that
We will.
instead
I got
of
you.
doing tasks.
I got you. We will. I got you. I got you. We will. We will.
Wait, because I need to write this down before you go through it. If not, I'm not gonna pass the test.
I can read it though, right?
Yeah.
Yeah. It's just the same thing that we just did. Yeah. Yeah. So look.
As long as you let me write it, I don't care.
Yeah, you got time. You got time. So look, next we will use table 3 of the appendix to find the z value corresponding to the left tail area of 0.005, right? So what they're saying here is like we found the positive z critical, z 0.99. We could have found the negative z critical, which would have been 0.0050. All right. Same thing. We would have just found a negative value and then you just make it positive for the positive side. It's the same thing, right? So you could kind of see it right here, how they have negative 2.58 and positive 2.58. That's what we found, those numbers, right? They rounded it to the nearest hundredth place. That's why it's 2.58. You know? It is supposed to be 2.575, but they rounded to the nearest hundredth place. That's why. Mhm. That's dumb, right? We're better than that, right? Yeah. So we see that the desired area for 0.0050 is exactly halfway between the areas corresponding to negative 2.58 and negative 2.57. Because the two area values are so close together, we use the more conservative z value of negative 2.58 rather than interpolating, right? So in fact, z for 0.99 is 2.576. However, the 2 decimal places we use the z value for 0.99 equal to 2.58 as a critical value for the confidence level. So for c equal to 0.99. So we have the probability that negative 2.58 less than z less than 2.58 is going to be similar to 0.99. And they do the same thing that we just did, right? But they're doing it off the negative side because they're looking for 0.50. 0.50 is in between negative 2.57 and negative 2.58. Add them together, divide by 2, boom. That's how you get that. Mhm. I got you. I got you. I got you. Let me just check something. Okay. Go ahead. Take your time. 3.
Professor, that says interpolate. Professor, that says interpolate.
Interpolate. When you take calculus, you'll learn what that is.
Professor, that's an equal sign that says 2.576.
Similar. Similar. So it's not equal to it, it's just similar to it. Like imagine that they're rounding off the answer or something like that. That's what it is. It's not the answer, it's close to the answer, something like that. Mhm. I see you.
So
Good luck.
one, two, okay, negative one instead. Okay, because I don't understand this, that's why I have to write it down.
Why? So remember how we had our area of 99 in the middle? And I asked you what's the tail end, and you said it would be 0.005, right? That's what they're looking up in the table. Just that area to the left. That's how they got that. So I looked up 0.9950, but they looked up the area for negative z, right? Which is 0.0050. Right?
So, okay, so that's where you got the -0.0050.
Yeah.
Okay, so -0.0050 would be where, so what table? 8?
That's 8.1.
Wait, what did they do? Hold on.
They looked up 0.0050, the little tail area that we found, right, when we did our example. They're looking up just that area to the left.
Oh, what makes them think that 0?
So what they're finding is they're finding the negative Z critical value. We found the positive Z critical value. So they're doing it a little bit different, but it's all good.
Hey, I'm on page A8.
That's it.
Okay, and what you want?
So 0.0050. Yeah, it's in the middle. Hmm? Yeah.
0.8. Okay, yeah, I did it.
That's it.
I still don't see it.
0.0.
So it should be at negative 2.58 and 2.57.
It's right at 51. Just like the other
Right,
one.
it should be a 51 and a 49.
49.
Right,
That's -2.57 and -2.58.
right.
Okay.
And add them and divide by 2. Yeah.
All right, hold on, let me do that on the calculator real quick, just to make sure I'm following.
Yeah.
So you want 0.0051 plus,
No,
Oh, wait, hold
negative
on.
2.57.
hold on a minute, you want 0.0051
No, negative 2.57.
plus -2.58
Right, and divide by 2.
divided by 2, so that's -2.575.
Divided by 2.
Yeah. So they're finding the opposite side. Go ahead.
Go up a little bit. It doesn't say -2.58 right there in the problem. It says 2.58.
Because they're rounding it off to the nearest hundredth.
No, not that. The one down here.
Right here, this one?
Yeah. It says -1 and then positive the other.
So you.
That's the way it is. You see how in my picture, we have two Z criticals, there's a positive one and a negative one? Right, so this would be the
But when we look at the table.
negative 2.575.
Professor, if you would write the problem down, I wouldn't have known that.
I got you.
You gotta try your best to give us time to write the problems down,
I got you.
cause that really helped.
It becomes -2.575.
Mhm.
But it's the same thing.
It's the
as
same
other
thing.
one.
But negative. That's the only difference. All right?
I thought we
Okay, but where did you get that? Where did you get? So that problem up there is not this
It's
problem.
the same thing. It's just that they're looking it up a little bit different, right? So look, we looked up this part in the middle, right? All they looked up was this part. And then they found that. That's the difference. Yeah. Negative 2 points. Yeah. Right. I'd rather look up the positive one.
Yeah.
No,
Why?
I don't like negatives, not even in my bank account. Yeah. Yeah. All right, so look, the results of example 1, right, will be used a great deal in our later work. For your convenience, table 8.2 gives some levels of confidence and corresponding critical Z critical values. The same information is provided in table 3B of the appendix. An estimate is not very valuable unless we have some kind of measure of how good it is. The language of probability can give us an idea of the size of the margin of error caused by using the sample mean X bar as an estimate for the population mean. Remember that the sample mean is a random variable. Each time we draw a sample size n from a population, we can get a different value for the sample mean, right? So according to the central limit theorem, let me finish that idea before I show y'all.
Yeah.
I got you. I got you. I got you. I guess that's enough. The mean, yeah, I got you. So according to the central limit theorem, let me get that big enough so that we could all see, right? If the sample size is large, then the sample mean has a distribution that is approximately normal, with the mean of mu for x bar is equal to mu, and the population mean we are trying to estimate. Okay. The standard deviation is sigma for x bar is equal to the standard deviation divided by the square root of n. If x has a normal distribution, these results are true for any sample size, right? See the theorem, right? So this information to put together with our work on confidence levels leads us to, as shown in the optimal deviation that follows, to the probability statement. The probability of negative z critical times the standard deviation divided by the square root of n is less than the sample mean minus the population mean, which is less than z critical times the standard deviation divided by the square root of n, which is equal to the critical value. All right? Okay. So I'm going to this is able to go ahead.
The sample size, we do this is equal to the norm. So the sample size, X distribution, the normal rate. And the population mean we're trying to estimate. Why we're trying to estimate, right?
Right.
And then the standard deviation is what?
That's going to be given to you. It's going to be given to you.
They're gonna give us the standard deviation.
Yeah. You have to calculate the margin of error. We don't talk about that. It's coming. It's coming. All right. But real quick. No. Real quick. So we just went through the whole process of how to find the Z critical, right?
Yes.
But on your formula sheet, you have this table that lists all the levels of confidence for you and the Z critical value that corresponds to them. This is table 8.2, right? It's right underneath your normal distribution table, right? So 8.2, yeah, that thing, yeah.
Tell me what.
Yeah. So this is what we just did, right? So remember, we just found Z for 0.99, right? We just found 0.99. Yeah, exactly. Right? And we said that this was 2.58.
70% or 75, 80, 85, 90, 95, 98, 99, the answer's right there.
Exactly.
Yeah, it's on the formula sheet.
Mhm.
Oh, yours doesn't have the nine.
Yeah.
In the back right here.
We just found that, so I just added it. Mhm.
Oh, thank God. Me too.
Let's see.
Then what does this say right here? So look, critical.
Tomorrow we'll talk about that.
Oh, okay, perfect. All right, that makes sense.
Wait, so we have today's Wednesday, so tomorrow we finish chapter 9.
Tomorrow we'll finish chapter 9.
And the test is gonna be 7, 8, 9. Oh, Lord.
What?
What? 7, 8, 9, what? Yeah, our test for next week is gonna be 7, 8, and 9. Chapter.
That's it, right?
I hope so, because the last test was diabolical.
That's none. Wait till you see test 4.
No, these kids are fine.
Huh?
I don't know.
Really?
That's what my psychology.
I don't think that's it.
teacher, my English teacher did.
It's only like 4 formulas. Yeah. I'll show you though. Don't worry. Got you, I got you. Yeah. Yeah. So look, equation one uses the language of probability to give us an idea of the size of the margin of error for the corresponding confidence level C. In words, equation one states that the probability is C, our critical value, that our point estimate X bar is within a distance of plus or minus Z critical times the standard deviation divided by the square root of N of the population mean mu. This relationship is going to be shown in the next picture, right? In the following optional discussion, we derive the equation, right? If you prefer, you may jump ahead the discussion about margin of error. So here we go. Let's get it, let's get it, let's get it.
I don't like the answer this. You actually uncomplicated this in a nice way.
Thanks.
Yeah, you did that. Thank you.
You're not staying?
No, I'm staying.
Okay.
I'm staying. I'm not going nowhere, but I understand.
That's good.
I'm not leaving.
So here you go. This is what I'm saying right here, right? So this is the distribution of the sample mean, right? So the probability is C. That's this area in the blue, right? X bar is within plus or minus the Z critical, right? Times the standard deviation divided by the square root of N of the true population mean mu, right? Long story short, but it is. It is. Yeah. So long story short, right? What this section is doing, right? I'm taking a sample from a population, right? For whatever reason, I can't calculate the population parameter that I'm interested in, right? For example, right? Um, let's say I want to know if New York City really likes Mondami as mayor,
Yeah.
right? Now, I don't have the time, the resources, or whatever to go ask everybody in New York City what they think, right? But I can ask all of you what you guys think. And I can use that to kind of represent what New York City thinks, you know, in a nutshell. The issue that I have, right, is how do I can't get what New York City thinks, but what I could do is I could come up with a range that New York City probably falls in between. That, right, like an estimate, right? That's what I'm doing here, right? I have some type of sample, but I'm not interested in the sample. I'm interested in the population parameter, right? Like I don't really care if the Bronx likes Trump. I want to know, does the United States like Trump? You know, for example. So let's keep going. I'll show you. There is a process that we do with that. All right.
I have my calculator ready.
I got you. So we gonna talk about the margin of error because that's what we're gonna do with it.
Just connect it to the Z,
Mhm.
critical levels of Z.
Yeah.
I wrote that down, by the way, but
Good.
I put my notebook away because I think I'm okay to just use the calculator right now.
Yeah, you good. It's all on the formula sheet.
It really is.
Yeah.
For the first time, I can agree with you.
Mhm. So the margin of error, right, or the absolute error, that's another name for it, using the sample mean as a point estimate for the population mean is the absolute value of the sample mean minus the population mean. In most practical problems, the population mean is unknown. So the margin of error is also unknown. However, equation one allows us to compute an error tolerance called E, right? That serves as a bound on the margin of error using the critical value percentage or the level of confidence, right? So we say that the point estimate X bar sample mean differs from the population mean mu by a maximal margin of error. This is your equation for margin of error. E equals Z critical times the standard deviation over the square root of N, right? And in case you're wondering, yes, it's on your formula sheet, right? So note, formula 5 for E is based on the fact that the sampling distribution for the sample mean is exactly normal with the mean mu and a standard deviation sigma over the square root of n. This occurs whenever the x distribution is normal with the mean of mu and the standard deviation sigma. If the x distribution is not normal, then according to the central limit theorem, large samples n greater than or equal to 30 produce an x distribution that is approximately normal with mean mu and standard deviation sigma over the square root of n. All right? I got you. I'm put it all together. Using equations 1 and 5, we conclude that the probability of the negative error is less than the sample mean minus the population mean, which is less than the positive error, and that's going to be equal to the critical value.
Less than 2.5 is equal to C, which is 0.99.
Right.
That's equivalent.
Mm-hmm.
Okay, but wait,
So-
you're going up, you're going up, go up, go up to the other one.
Which one?
The money. Because we were written
Mhm.
that formula, right?
Mm-hmm.
We have to like input what you gave us into that formula.
Right. And then you get the margin of error. Right? It'll make more sense when we get to the example. Right? So equation 6 states that the probability is the critical value that the difference between the sample mean and the population mean is no more than the maximal error tolerance, which is E, right? If we use a little algebra on the inequality, we have negative E less than the sample mean minus the population mean less than the margin error E, right? Let's look at what happens when we use a little algebra on it. This is going to be good.
So E is 2.58
And 2.57? Or,
Mm-hmm.
so it's a negative and the positive 2.58?
Yeah.
And why is that?
then X would be,
Because the critical value is in between two of them. That's why there's a negative and a positive.
No, I mean, our values were 2.57 and 2.58, so why did you choose 2.58 to be E?
It was 2.575, and it rounds off to 2.58. Remember, we had it in between the two numbers, so we just rounded off to the nearest 100th place. Yeah.
2.57 to 2.58
2.575.
to 2.58,
Right,
because it's 7 and a 5,
right.
so it goes
Yeah,
up.
yeah.
we kind of was X and was E.
In the question, they'll give it to you. Yeah. So X bar is your sample mean, and mu is what you want to know.
Can you actually?
Right? That's what we want to know.
Really?
Really? I got you. Yeah, we're gonna get to it. Not everybody else. All right. So like for mu, we can rewrite it in the following mathematical equivalent way. X bar minus the margin of error is less than mu, which is less than X bar plus the margin of error, right? This is what's on your formula sheet, right?
Yeah, I saw that.
So since formulas 7 and 8 are mathematically equivalent, their probabilities are the same. So therefore, from 6, 7, and 8, we obtain that the probability of X bar minus the margin of error less than the mean mu less than X bar plus the margin of error is equal to the critical value, right? Equation 9 states that there is a chance, critical value, that the interval from X bar minus the margin of error to the sample mean plus the margin of error contains the population mean mu. We call this interval a confidence interval for the population mean, right?
Equation 9 is chapter.
No, this is all chapter 8.
Professor,
So yeah,
the problem that we did.
yeah. Well, no, I'm gonna give you guys a fresh problem, right? Yeah, it'll make sense. It'll make sense. What's happening here though, real quick? All right. I have some population. Every time I take a sample from that population, right? that population might contain the population mean or it might not contain the population mean, right? What I'm doing with this level of confidence, right, is I'm saying that I believe the sample that I just took might contain the population mean 99% of the time or 89% of the time or whatever percent of the time, right? That's what this is doing, right? Right. So the best I could do is I could give a range that the population mean might fall in between, right? The wider my range, the more confident I am that the sample contains it. The closer my range is, the less confident I am. That's it. Right? We building up to it. We building up to it.
An appointment.
No problem. You can go. I'm recording it.
Just leave.
So a C confidence interval for the population mean mu is an interval computed from sample data in such a way that the confidence value is the probability of generating an interval containing the actual value of the population mean mu. In other words, right, the confidence value is the proportion of confidence intervals based on random samples of size n that actually contain the mean mu, right? So we may get a different confidence interval for each different sample that is taken. Some intervals will contain the population mean mu, others will not. However, in the long run, the proportion of confidence intervals that contain mu is the critical value. Right? But in English. Right. So before we get into we get into an example, let me just give y'all the procedure of how you do this. Step by step. Well, first let me tell you how to do it. First let me tell you how to do it. Because that was a lot of information. Right? I'm gonna bring it back. Hold on. So first, I want to tell y'all how to do it. So this is how to find a confidence interval for the population mean mu when sigma is known, right?
When sigma is known.
When sigma is known, right? So here are the requirements. Let X be a random variable appropriate to your application. Obtain a simple random sample of size n of X values from which you compute the sample mean X bar, right? The value of sigma is already known, perhaps from a previous study. If, right, if you can assume that X has a normal distribution, then any sample size n will work. If you cannot assume this, then use a sample size of n greater than or equal to 30, right? Confidence intervals for mu when sigma is known will be written like this. X bar minus the margin of error less than the population mean mu less than the sample mean plus the margin of error, right? Where X bar is equal to your sample mean of the simple random sample, and the margin of error E is equal to Z critical times the standard deviation divided by the square root of n, right? Where C is equal to your confidence level, which is between 0 and 1. All right. Z critical is the critical value for the confidence level C based on the standard normal distribution, right? And we can see that from table 3B of the appendix. All right. Now let's look at an example. That little table with all of the thing. Yeah. Let's look at an example.
You better have like 5 questions within this time.
For this, you'll have like one. You're gonna have like one question on this.
You know, Professor such and such failure.
I gotcha. So look, confidence interval for mu when sigma is known, right? Let's say that Julia enjoys jogging. She's been jogging over a period of several years, during which time her physical condition has remained constantly good. Usually she jogs 2 miles per day. Damn. The standard deviation of her time is sigma equal to 1.8 minutes. Damn. During the past year, yeah, 1.80 minutes. Mhm. During the past year, Julia has recorded her times to 2 runs. She has a random sample of 90 of those times. For these 90 times, the mean was X bar, excuse me, equal to 15.60 minutes. Jesus. Let mu be the mean jogging time for the entire distribution of Julia's 2 mile running times taken over the past year. Find a 95% confidence interval for mu, right? Exactly.
95% equals?
Exactly. So it's easy, right? So the first thing we got to do, right? We have to find our margin of error, right? Now we know that our margin of error, I can't spell.
Isn't okay, so would the margin of error be 1.80 or 2 miles?
No, look, it's your E formula. E is equal to Z critical times the standard deviation over the square root of N. Right.
The C critical is gonna be what's next to 95% on formula sheet, right?
Exactly. But real quick, before we jump into this, let me just show y'all where this is on the formula sheet. As soon as I figure out where my formula sheet is, 1 second.
Like,
I have it. It's just somewhere. Oh, here it is. 95%. I don't know, but we gonna figure it out. So look, this is where my margin error formula is. All right. E is equal to Z critical times standard deviation over the square root of N when sigma is known. My final answer looks like this, right? It should be some interval like that, right? Now we want to find a 95% confidence level, right?
So that's the box.
So go to your table right here where it says confidence intervals. You go down to 0.95 and it's 1.96.
So at the Z
Right?
plug in,
Right.
1.96. Plus we already got the U and the X mean.
Exactly. So I know that Z critical or not even critical, right? Z for 95.
Not yet.
Okay, and then the next step is to go to the table, right?
Right. To find what the Z for 95 is, which we know is 1.96, right? We were given our standard deviation right here. We were given our sample mean right here, right? We were given our N right there. That's our 90.
Our N is X.
No, X bar is 15.6.
Are we going to do 1.96 times 1.80 divided by the square root of N?
Yeah.
Wait, Professor, so N is what? Is 1 point?
It's 90.
Oh, that's N?
Yeah.
Why is N 90, Professor?
Why is it?
Is that's all the
90 times.
samples.
90 times, yeah. That is the samples, 90 times total, correct?
It's the random sample of 90.
So 196.
That's why.
1.80. Wait, first of all, let me square root. When you say square root of 90, you want me to do like what times what equals 90?
No, second square root, 90. Wait, I'm sorry, just turn it sideways. Oh yeah, that one. So just 90 and then square root. I don't know, square root X somewhere. Yeah, that's it.
9.48.
That's it. Yeah.
So I'm doing 1.96 times 1.80. Divided by 9.48, correct? And that's 0.36.
I guess.
Professor,
I'm
why are
not-
you so disappointed in me?
I'm not that good at math. I don't know.
Yeah, times 1.80.
So is
And then divided by the square root of 90. And then divide by the square root of 90. Yeah. So let's see if I That's probably it. But hold on, I wanna do it on the calculator just to verify that I get that.
If I got that right, that's crazy.
You
If I
probably
got that,
did.
I'm walking out of here.
You probably did. But I just want to verify it on the calculator real quick. So let's verify this.
Jeez.
But you didn't, oh, you just got.
No, I just never wear the label.
No, girl, that happens when you just get it. Oh, right now,
This part fits me big, and this part's like.
yeah, that's hard. It'd be hard for me to put on mine too, girl.
So
Yeah, girl, what's the problem?
Jesus.
It's gonna get better, don't worry.
Oh, that too.
You fucking serious. I put on socks with my.
I didn't have tights on though, because these tights are see-through.
But why you
These are, look, I bet you people think they looking at my ass.
Oh, those types are see-through.
So you have to square it, Professor, when you put it in, right?
Yeah, you got.
Right. So I'm just typing it in to make sure we all on the same page.
If I did this right, I'm gonna be very impressed with myself.
So E equals.
I don't mind my calculators.
That's what you got, right?
Oh, 0.366, but if I round it off, isn't it the same thing?
You are, too. Let me try it in my
I got
calculator.
0.3188.
So I accidentally put
Three.
93, was a typo.
Number.
I'm gonna round it off. 9. The calculator gave me all the numbers, so that's why I'm writing them. I just like to. Technically speaking,
Yeah.
you only really need to put up to the thousands place because you want to round off to whatever your mean is. Go ahead. You got the same thing as me?
Oh, yeah, I accidentally put 193 instead of
Got it.
196. It was just a typo. But
Gotcha.
I know exactly.
I would rather just let the calculator do all of it for you.
Oh,
Mhm.
I'm on that calculator today.
I got you, it's fine.
0.371.
372. I would accept that.
What if we just put the whole number in school?
That's what I like.
Put the whole number, yeah.
I don't like rounding. I don't like rounding.
So this is not bad if he gives us the numbers.
Always you'll get the
Are you gonna
numbers.
give us the numbers on the test?
Always.
You're gonna do some bullshit.
Always you have the numbers. So now look, you found the margin of error, right? So now we're gonna finish the problem, right?
What the numbers?
At the end, yeah, because I ran out of space. But look, our answer. Go ahead. I'll catch up with you. Our answer is gonna be X bar minus the margin of error, less than the population mean mu, less than X bar plus the margin of error, right? All you have to do is just write in the answers, right? So we know that our sample mean is what, 15.6. Just plug it in. 0.60 minus 0.3718839, whatever, less than mu, less than 15.60.
You did.
So mu is what I want to know, but I can't know it.
Professor, why you?
I can only do sorry. But I can't get it. I can only do a range for it. So very simply, let's do this out, right? So this is 15.6 minus minus the 0.
So we're gonna add this stuff?
First subtract and then add. Yeah.
So,
Because the formula told us to. So, so this is 15.22812, whatever. Less than mu, less than, then you're gonna add it. So 15.6 plus the 0.39, whatever. So then I got 15.6 97188. All right. Because my sample mean was to the nearest hundredth, you can round this off to the nearest hundredth. I personally don't like to round. I'm okay with this answer, but I would accept because of the sample mean, I would accept 15, yeah, 0.23 less than mu, less than 15.97. So, yeah, right. I would accept any one of these answers. But which one do I prefer? This one,
Let's sit here.
right?
So you go there.
Oh,
And that's it.
yeah,
That's it.
that's fine. All right. All right. I see you. All right, man. Thanks.
Thank you. I'll see you tomorrow.
All right. See you. You're welcome. All right.
But I think tomorrow, can we go over the last part more?
Hmm?
Cause you know, we kind of did it like planning out a class, so
I
I
got you.
guess the final plugin, I still kind of need you to like go over that with me a little bit, and I can't stay, I have a cycle dinner real quick.
I got you. No problem.
I like that. You know what?